sometimes recipes, when it says how many brownies or how many cookies something will make, they'll call it the yield. Okay, so actually, whenever you do a stoichiometric calculation where you are going from, I'll put a R for reactant, to question mark product, you are coming up with what we call a yield. That's a yield stoichiometric calculation. More specifically, it's called a theoretical yield. So it's in theory what you should get back. So we've actually done some theoretical yield stoichiometric calculations. All you're doing is starting with a reactant and seeing how much product you should form. Okay, now like this slide says, that theoretical yield is actually an upper limit. Usually, and I'm going to give you some examples why, but usually your, how do I say this, your reactant kind of doesn't entirely 100% find its way to form product. We'll talk about why that is. Usually your yields are low. Reasons why your yields might be low. I'm going to kind of talk you through each one of these, but just to kind of give you an overall view. Reaction kinetics has to do with speed. Sometimes it just takes too long for it to, what we say, react 100%, for your reactants to go 100% to products. Sometimes I say we get too impatient to wait for all of our product to form. Another one, in this you're fighting a battle of basically it's going this way, your reaction's going this way, but there's a lot of reactions and they're kind of, I guess, not all that strange, but they actually also go, what we say, from right back to left again. So if this is reactants and this is products, you're never going to get 100% products because you have some converting back to form reactants. That's called a chemical equilibrium. Sometimes you have an unwanted sort of side reaction. When we reacted magnesium with oxygen to form magnesium oxide, actually in the background information it said a side unwanted reaction was where magnesium actually combines with nitrogen in the air to form magnesium nitride, Mg3N2. So that is an example of you just can't help it, right? Again, something that you can't help are physical losses. Now these would be, I'll try to explain, these aren't the oops loss, like I spilled it loss. These actually are inherent in the experiment. Like sometimes you just know that because of purification or because of, well, mostly purification, but you're just not going to get all of your product. So yields are usually less than 100%. I mentioned reaction kinetics. Reaction kinetics, and you're going to want to know a little bit of this for your test, but reaction kinetics is time. Takes too much time. Okay. I think I have an example here. For instance, we assume that reactants go to form products like right away. Well, here let's see, the reactants are in red. Okay, and you see time ticking away over here along the x-axis. So of course your reactants are going to go down, down. This is the concentration, molar concentration. And your products are going to go up, 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 up. Well, this example says, well, what if we stop about 7 seconds? So 7 seconds, let's see, that's 5, 6, 7 seconds is about here. Okay, so at 7 seconds, look, you have about half of your reactants have gone to form products. So if you stop it too soon, then your yield here at 7 seconds, in other words, is going to be what, 50%? Because it's half of what you thought you should get. This is the back and forth sort of thing, the chemical equilibrium. There are more things than you think that are actually go, what we say, from left to right and from right back to left again. So the example I have here is this reaction of H2 and I2. Okay, so notice that if your product is HI and you have two reactants, H2 and I2, that you're never going to get 100%. It's always going to be less than 100% because some of your HI is going to go back to form H2I2. This example I have here, or that's in this figure here, is let's say you have a certain amount of H2I2 and it's going to go to form your HI. At some point in time, you're going to have HI, H2I2. Basically, the concentrations or molar concentrations are going to level off, and they aren't going to change any. So this is the end. This here is the end. This is time. Okay. So at the end, you're always going to have some of the reactants left. Okay, competing reactions. I kind of mentioned the experiment you guys did with your magnesium. You know, an unwanted side reaction would be it reacting with nitrogen to form magnesium nitride. Physical losses here. I mentioned purification. You know, it's not the oops. Oops is gross error. Oops. Okay, so. Physical losses is not oops. Okay, it's basically what I said, inherent or built into the experiment. It's unavoidable. Okay, so this is my little thing here. This topic always makes me think of pharmaceuticals. You know, and I don't know much about it, just enough to be dangerous. But in the lab, it takes. You always know that there's a trade-off, like the slide says. The more pure you want your product to be, you're going to have to lose some of your product in the purification steps. So that's why I think about pharmaceuticals, is they really are very stringent with they can't have anything other than the medicine. They have to be very pure. So anyway, there you go. So when you calculate a theoretical yield, okay, when you do a stoichiometric calculation, just to remind you what that is, a theoretical yield is basically all it means is that you have picked a certain amount of reactant and you're focusing on one product. That's a theoretical yield. So those are kind of an upper sort of end of amount that you'll get back with regard to product if all of the reactant, especially the limited supply, I'll kind of talk about what I mean by which reactant is limited supply, but if all of the amount of reactant reacts, and that if there are no side reactions, okay, and that if you're able to recover all of your product. So yeah, it's a lot of ifs. Now this is the oops error, and I do want to kind of talk a little bit about that. Oops errors are not built into the experiment. That means that, and this uses the painful word ineptness. Okay, the experimenter did something wrong, basically. So what sort of things could you do wrong? Well, for instance, you could spill some material. That would be a gross error. You could read, and we've all done this. We've all done all these. You could misread an instrument, and that would be a gross error. You could do something wrong in your calculations, and that would be a gross error. Or finally, you could maybe not run through the experiment as it's presented to you, not follow instructions, and that would be a gross error. So these are all things that were avoidable.